Hello everyone and welcome to session 8 of Porous Material 101 via MATLAB. In today's session we're going to talk more about pore size distribution. So if you have followed this sort of trainings, we have talked about how to create some geometries, how to segment them. So we're going to use those pre-developed functions. As you can see here in my current directory, I have those pre-developed functions, and then I write all of my code inside this main file, so you can then access it later from the GitHub link in the description. So let's start by creating a geometry, an overlapped sphere geometry. So we just put that geometry inside this array A. And then we wanted to simply visualize it to see how does it look like. So if we run this part of the code, yeah, this is the result. As you can see, this is the geometry we have made. There are some spheres that they have some overlappings. And now we wanted to find the size distribution of these tiny little spaces between these spheres, as you can see here in the image. Okay, so in order to do that, we use a function that we have developed previously known as segment. It uses watershed segmentation algorithm to break down a large structure into smaller structuring elements. So we just apply segment on the array A, and we put the results in this labeled array, which we call L. And then we can simply use the surface function that we have also previously developed here. And if we can simply run this part of the code, you can see this is the results. These are different pore spaces segmented from each other and labeled with different colors, so you can detect them by eye. And now we can use this 3D map to find the structural elements properties, for example the size of these elements or many different properties as you wish. So now just don't forget that these images, they have a spatial resolution. It means each of these pixels inside this image or voxels, they have a physical meaning. So we have assumed that the spatial resolution of this image is 5 micron per pixel or per voxel. It means each of these voxels would represent 5 microns in the real world. So in order to find the properties, as you have seen in the previous session, we use a function known as region props, which is a built-in function inside MATLAB, and then the output of this region props function is a structure that has a specific field known as area, and using that area, which shows the volume of those pores, we are able to back calculate the equivalent radius of these pores, of each of the pores, and then we multiply this value by the spatial resolution, and finally we are able to visualize the pore size distribution of this geometry using the histogram command, which is also a built-in function inside MATLAB, and then we use probability as a normalization method for visualizing this data. As you can see here, we have the pore size distribution. We have a peak around 20, about between 10 and 20 microns, and then this shows the probability, and the summation of all of these columns is equal to 1 based on the definition of the probability. So if you want it, we can also fit a distribution on this data and see how does it look like. So I recommend, instead of using normal distribution, we use log normal distribution for this sort of data, because logically we do not have any negative pore size, which it makes sense if we use log normal distribution because it automatically ignores the negative values. So if we evaluate this part of the code, you can see that this is the distribution, side distribution, and this is the fitted function, and it's got a long tail in the positive side of the axis. Okay, so if we wanted to find out the pore size, actually the size distribution of the granular space or the particles, we just simply need to invert the geometry. So originally our geometry was like this, that 1 represents solid and 0 represents the void space. But if we just invert that geometry, we can calculate all the same stuff for also the solid space. So it would be particle size distribution, or we can call it grain size distribution. So we simply needed to repeat different stages for the solid space. The only difference is that instead of segmenting the array A, we segment the array 1 minus A. And we just repeat all the same steps as we have done it before. And this time I've decided to plot both pore size and grain size distributions at the same time, so it can give you an idea that how is different properties of your porous material. Okay, so if we evaluate this part of the code, let's wait for the result. Okay, yeah, as you can see, this is the pore size and grain size distribution at the same time. As you can see, the grain size distribution is a bit larger than the pore size. It's a bit shifted onto the right side of the axis, and also here we have the segmented structure of our grains. As you can see, we had some overlapped spheres, but here some of these spheres has been distinguished from each other and has been separated. And also here we have the segmented map of each of these spheres, which somehow they're not actually spheres right now, but some of them are. So we can call them grains. So as you can see, we have labeled them with different colors and they're visualized in this figure. And here is the pore size and grain size distribution at the same time. Thank you very much everybody for watching this session, and I will see you in the next session. Bye.